So signaling games. Some entities have information, send signals to other entities, right? The receivers react to the signals somehow, right? Payoffs, well, the signals might be cost-free, in which case you might have common interest between senders and receivers. Some people look at these models. You might have diametrically opposed interests. Very few people look at these models because they figure nothing interesting will happen. And you can have mixed interests, and they're very influential models with mixed interests. And then signals might have differential costs, which are the heart of the costly signaling literature in evolutionary biology, the Zahavi models and costly signaling literature in economics stemming from Spence. Signals need not just be between one sender and a receiver, but can be between many entities arranged in various topologies, so all sorts of things can happen. Today, I'm only going to focus on the simplest games, right? But there's a big space out here, okay? And some things are known about more complicated things, including Bill's, let me refer back to Bill's talk, right? For dynamics, there are all sorts of adaptive dynamics, evolution, imitation, and learning. And today I'm going to focus on three dynamics. One is a large population dynamics, and we're going to look at the replicator dynamics as a large population random mixing dynamics. One is a small population, fixed size population, and we'll look at the frequency dependent Moran process for that population. And finally, individual learning, and I'll look at individual reinforcement learning of a certain kind, which is different than the kind Bill talked about. It's what you referred to as EARN models, and you might think for populations that are finite, you don't want a fixed size, but you want a growing size, but that actually has, those models have close connections with the individual learning models. So this talk will be just some snapshots of dynamics for some simple signaling games to give a taste of various things that can happen. So first, the infinite population. We'll use the replicator dynamics with a small excursion into selection mutation dynamics, throw in a little mutation. Here's the replicator dynamics. The x sub I is the proportion of the population playing strategy I. And so the time derivative of that is x sub I times the average fitness of that strategy minus the average fitness of the population. Okay, so that's the replicator dynamics. And of course, average fitness, you could expand. Expand in the usual way if you assume random matching in the population, but you don't have to assume that. Whatever gives you average fitness goes into that equation. So that's the replicator dynamics. And the first game I want to look at is a game of common interests, right? And then later we'll look at opposed interests and partially aligned interests. So here's a simple game, a simple signaling game of common interest of the kind introduced by David Lewis in his book on convention. Nature flips a fair coin to choose state 1 or state 2. A sender observes the state and sends signal A or B. These signals are not assumed to have any pre-existing meaning. The receiver observes the signal and guesses the state. A correct guess pays off 1 to both sender and receiver, nothing otherwise. Okay? And this is supposed to be a model as to how meaning of signals could arise spontaneously. Okay? In the same vein as the naming game, but a different model. Okay? There are two kinds of equilibria in this simplest Lewis signaling game. Signaling systems in which either A or B means state 1 and the other one means state 2. Okay, so there's one signaling system on the left, the other signaling system on the right. Or pooling equilibria, where the sender's probabilities are independent of the state, the receiver's probabilities are independent of the signal. Sender's probabilities for sending signal A, let's say, go from 0 to 1, can go from 0 to 1. Receivers for guessing A can go from 0 to 1 for each signal. So we have a whole connected component, a square, if you please, of pooling equilibria. Right? These are the only equilibria in this game. Now, if we look at this game and apply the replicator dynamics, now we'll apply replicator dynamics to two populations because there's a population of senders, there's a population of receivers. They're paired. The sender sends, nature flips a coin, chooses the state, sender sends a signal, receiver sees the signal and guesses the state. Payoffs now are fitnesses, and they derive the replicator dynamics. Okay. The pooling equilibria are all dynamically unstable, okay, in replicator dynamics. So the result is something that David Lewis would have liked very much. Signaling systems emerge spontaneously from almost every starting point in the polytope of population proportions for the two populations. So you're sure to get signaling, but this model isn't structurally stable, right? It isn't structurally stable because you've got this connected component of pooling equilibria where no information is transferred from the sender and the receiver. And on this square, if you please, this connected component of pooling equilibria, if you perturbed the dynamics at all, you'd make a big change. Right? So we really should think about perturbations of the dynamics before we simply go home. So, first perturbation I'd like to talk about is, let's suppose the states aren't equiprobable. I assume nature flipped a fair coin. Well, maybe nature flips a biased coin. Right? Well, then it isn't true anymore. If you look at the equilibrium structure, the component of pooling equilibria collapses from this square to a line. Right? If there's pooling, the sender's probabilities are independent of the state, and the receiver then on this line does the act that's best for the most probable state, right? Guesses the most probable state, right? And those are now the pooling equilibria. But now if we look at this line, the points on it aren't all dynamically unstable. The points in the interior of the line, in fact, are stable, right? They're stable. The points next to them, of course, stay next to them. But what's more interesting is that the points in the interior of the polytope that are close to them get attracted into this line. Okay? Pooling has now a positive basin of attraction. Okay? You don't always learn to signal. But this model isn't structurally stable either, right? Because it's got this line of pooling equilibria, right? And there's no selection pressure on the line, so if you changed the dynamics a little bit on the line, you could change everything, right? So I'd like to look at another perturbation of this model. And we can think of this as mutation if you're doing biology, or experimentation if you're doing some kind of social learning in a large population. So then the replicator dynamics, we're still thinking of a big population, so we're doing differential equations. The replicator dynamics is now replaced by the selection mutation dynamics. Okay, we put in a mutation term. I show it later if anybody wants me to, but I'm just going to go right through. Okay. And the mutation rates or expectation rates, since this is a two-population model, might be different for the two populations. They might be the same, they might be different. Okay. So we'll have an experimentation rate for the receivers, epsilon, and one for the senders, delta. Okay. And now, because mutation tends to drive you away from the borders of the simplex or the polytope into the interior, right? This line collapses to a single point. Oop. Have I done it? Oh, no, that's good. So the pooling equilibria, the line of pooling equilibria now collapses to a single point. Okay? And the question is, if you're interested in, like Lewis and other philosophers, about the spontaneous emergence of meaning in these games, is this an unstable point, a stable point, or a strongly stable point in the dynamics? And the answer is, well, it depends, right? It might be one or the other. So the analysis done by Josef Hofbauer and my colleague Simon Hudiger in Journal of Theoretical Biology, 2008, it depends on the ratio of these experimentation rates, right? If we have this inequality satisfied, we have a sink. That means that this pooling equilibrium point attracts things around it, right? So we can't just think that it doesn't matter, right? But if the inequality is reversed, it's a saddle, right? Which is dynamically unstable, and things near it get carried away from it, and then we learn to signal with probability 1, right? Well, to signal out perfectly, because a little bit of mutation is moving you a little bit off of the signaling equilibria, but close enough for jazz. For learning to signal, it's better if the experimenter experiments, if the receiver experiments a lot more than the sender, right? If they experiment, if delta equals epsilon, so they experiment the same amount, then if the disparity in probability of the states is not too great, you have an unstable pooling equilibrium, and you still learn to signal with probability 1. But if the disparity in states is too big, then there's a bifurcation. It becomes a stable equilibrium. And you don't learn to signal with probability 1. And that happens, so if delta equals epsilon, that happens when one state is maybe a little bit more than 75% of the time. So close to 50-50 and pretty far away, you're still okay, right? But you have to pay attention to this. Okay. So this is a game where you have pure common interest. Either both guys get paid off, right, when they're successful, or both guys get nothing when they're unsuccessful. What about opposed interests? If we have opposed interests, then we'll have zero-sum payoffs, right? The sender gets paid when the receiver doesn't, and vice versa. So in these games, the only equilibria are equilibria of no information transfer, right? Because if the sender encoded any information about the states in his signal, the receiver would then exploit it, right? So think about any other supposed equilibrium. It's not an equilibrium by that kind of reasoning. No information transfer in the only equilibria. And so many people have thought, well, nothing's going to ever happen in these games, right? they're not interesting. But they are interesting because if you look at the replicator dynamics, it might not ever reach equilibrium, okay, and is well known for some time. Whoop, whoop, back one. We want cycles. So if we give the sender and the receiver payoffs from matching pennies, so this says, you can read this, so in state 1, if the receiver does act 1 or guesses that it's state 1, then the receiver gets a 1, but the sender gets a 0. Right. Okay, so you can read this way, and they have perfectly opposed interests. The only Nash equilibrium, well, I haven't said what the game is, but this is the payoff for signaling. Okay. If we look at the subspace where the sender and the receiver use separating strategies, that is, sender sends a different signal for each state, receiver guesses a different state for each signal. Look at that subspace of separating strategies. What you get in these are cycles. Right? There's a Nash equilibrium right in the middle of it, which is a point of no information transfer. But you don't get to that. You start at any other point, and you get in cycles around this. So this is well known, right, from matching pennies, right? And it's just an application of matching pennies to signaling games. But these cycles, I suppose I should learn how to just have these pop out of the air, right? But these cycles are not structurally stable, right? So again, we want to look at something that's a little more robust to see whether this is just an artifact of some non-structurally stable model that somebody thought up. Here are payoffs that don't look too crazy for a signaling game. Now there are 3 states, right? And there are 3 acts the receiver can do, and it's still a zero-sum game. So we have perfectly opposed interests. Okay. But if this is the game, and we look at the subspace where the guys are using separating strategies, now we could have 3 strategies for the sender, 3 strategies for the receiver. We project down onto those things, and we have to imagine what's going on at these 2 things at the same time if we're not good at high-dimensional imagination. And it looks something like this. So we get a chaotic dynamics now. And 1, it is structurally stable. Right? 2, if you're close to this in the polytope that has all of the strategies in it, you can get sucked into it. So this is Elliot Wagner from here, right? Did this signaling game in the British Journal for Philosophy of Science in 2012. He builds on work of Sato, Akiyama, and Farmer, who find this Hamiltonian chaos in 2-population replicator dynamics, but not in a signaling game. Right? Well, okay, so in this sort of a setup, equilibrium analysis might lead you to believe no information transfer, not interesting, right? But there's lots of information transfer going on. But it's a kind of a Red Queen information transfer. Sometimes the sender's ahead, sometimes the receiver's ahead. You know, sometimes one guy's doing better, sometimes the other guy's doing better. They're chasing each other all over the space. If you have mixed interests with differential signaling costs, then equilibrium structure is pretty interesting, and it has been well studied in economics and biology. But non-equilibrium behavior can also be interesting you can get cycles in a non-trivial way in both the best-known economic signaling game, the spent signaling games, and as Spence himself suggested that there might be cycles, they're investigated in a certain dynamics that's built on Spence's market model by Noldike and Samuelson, and Wagner has a paper using replicator dynamics and best response dynamics, right? And gets cycles in replicator dynamics in the Spence signaling game, and you also get it in the Sir Philip Sidney game, which is a version of the Costless signaling literature in biology. Here's a picture of a subspace, right, where it shows orbits getting sucked onto the space where you have the cycles, right? So there is an equilibrium called the hybrid equilibrium right in the center there, right? It's the only equilibrium on this face, right? There are cycles around it, but it isn't just the peculiarity of this face. It's the fact that you get a lot of the interior of the polytope of population proportions can get drawn onto this face and onto the cycles. Okay, those are my snapshots for replicator dynamics, infinite population. Now I'd like to move to finite population. And the dynamics I'm going to look at is frequency-dependent Moran process with rare mutations. Okay, and I'll explain what that is, right? There are other finite population models. But I'm not going to talk about them unless you ask me to. So here's the frequency-dependent Moran process. There's some base game. Everybody plays it with everyone else to establish fitness. Okay? And for the results I'm going to talk about, it's a round robin, right? It's not random matching with fluctuations and that we have to analyze or anything. Okay, so fitness is there from the game interactions. One individual leaves, or average fitness, one individual leaves the group, okay, if we're thinking about imitation, or dies if we're thinking about biology, and a new one walks in the door or is born. The new individual imitates a strategy in the population with probability proportional to its average success in the population. Okay? So this Moran process was actually introduced without the game and the differential fitness due to the game as a model of neutral evolution. But then Fudenberg, Imhoff, Novak, and Taylor have an article introducing it in just this way. Okay, so that's the basic process. What's the basic process like? Well, it's a Markov chain. The state of the Markov process is the number of members of the population playing each strategy. And monomorphisms of the population, where everybody plays the same strategy, are the unique absorbing states. We can make it more interesting if we add mutation. So let's suppose that the new member who is born or who walks in the door with some probability chooses any strategy, including strategies that may be extinct in the population. Okay? Then there are no absorbing states. We have an ergodic Markov chain. Hard in general to analyze these chains to get the exact limiting distribution, right? If there's any complexity to any size to the population, any complexity to the model. but we can look at the small mutation limit, okay? This is the proportion of the time we study the proportion of the time a population spends in states, right, in the ergodic distribution, and then we take the limit as the mutation rate goes to 0. So we have rare mutations. Okay? It turns out that under these assumptions, maybe some not entirely spelled out yet, but under these assumptions, we can study transition probabilities between monomorphisms. It's assumed that that mutations are rare enough so that only one of them happens at a time, right? And then a long time goes, and then another one pops up. If you have lots of mutations all the time, it's a different ballgame. But if you have these assumptions satisfied, you can study transition probabilities between monomorphisms that are initiated by one mutation. One new guy walks in the door, right, with a new strategy. Things go, as said before. Does his strategy take over the population and take you to a new monomorphism, right, or not, right? What's the probability of that? And we do these probabilities of transitions between monomorphisms, and you can analyze those and get this. Okay, so this makes the thing tractable in a way that the general problem isn't. Okay, so that's our dynamics. And here's the game that we're going to apply this dynamics to, another signaling game. Sender is of 1, 2 types, high or low. Sender sends one of 2 signals, and these are cost-free signals here, and they have no pre-existing meaning. The receiver has 2 acts, one which she would prefer to do if the sender is a high sender, the other if it's a low sender, right? Think of the senders as males, right, and the receivers as females. You get but the sender would always prefer to be treated as a high-type sender, right? Now, in this game, as described, the only Nash equilibria are pooling equilibria. Because if the receiver discriminates at all among senders according to the signal, the sender will simply always send high. So nothing interesting, right? If you wanted something interesting, you put in cost, differential costs or something maybe. So here's a particular example that we'll use, this numerical example with these payoffs. It's still true that the only equilibrium is no information transfer. We have to specify the probability of the high state. We'll make it 0.4 just for a numerical example. To deal with this using the Imhoff Fudenberg technology, this works for one population, so we need it to be a one population game. So we have to symmetrize the game. Okay? Players, nature chooses you whether you're a high or a low type in a certain situation, right? Flips a coin. Right? And your strategy in the game has to be do this if you're a high type, do this if you're a low type. Okay? So that symmetrizes the game. Now we can look at it as a game in one population, and we'll choose the population size to be 50 here to get something that's a finite population, not very big, but not nothing either. Here's the long-run behavior in the limit, small mutation limit. There are only 2 Nash equilibria, 2 ways of pooling. This is one of the Nashes. Those are the other Nashes. Separating, as we've seen, that is information transfer, certainly not perfect information transfer, is no equilibrium at all. And yet, the system spends more than 50% of its time in separating equilibria, right? Well, things are very different if you look at things this way. Right? Not your father's game theory. There is some related work on costless pre-play exchange of signals. And here the situation is there are two guys who are going to play a two-person game. Each sends the other a signal. The signals don't have any pre-existing meaning, right? So they exchange these signals, they look at the signals, then they play a strategy in the two-person game, okay? Should the signals make any difference? Well, they don't cost anything. People can say anything, right? So you might think on the top of your head, right, that they shouldn't make any difference, but they can make a difference. They make a difference on the size of basins of attraction, even in the infinite population model, in the stag hunt. But in the stag hunt and in the prisoner's dilemma, second being kind of a surprise, you can spend a lot of time cooperating when you have pre-play signals. They make a difference, and the more signals you have, the better. So if you have lots of signals, right, and do this kind of small mutation limit analysis, right, even in the prisoner's dilemma, you can spend most of your time cooperating. Okay, that's my finite population model, and here's my learning model, individual learning model. Reinforcement learning a la Herrnstein and Roth and Erev. So Herrnstein's matching law is the probability of a specific choice is proportional to the accumulated rewards from that choice in the past. Okay, so that's what we're going to use. I know, and I know that lots of you know, that in Herrnstein the matching law can mean a lot of different things, right, depending on what you're reading. But this is what we mean. And this is what Roth and Erev used to model some learning in zero-sum games, digging up old work of Suppies and Atkinson, right, and applying this learning model to explain learning in zero-sum games. Okay. Some of the Roth and Erev models have lots of bells and whistles in them, but there are no bells and whistles here. This is just it, right? There are no recency effects, there's no errors, this is it. Sorry. It's commutative in the sense that if you're reinforced, it doesn't matter, it's just the accumulated reinforcements. Okay, that's the sufficient statistic. Okay, and it doesn't give you probability matching in bandit problems, which that was Bill's unsupervised learning, right? Or maybe it wasn't your unsupervised learning, but it doesn't give you probability matching where Bush-Mosteller does. Okay, so it's quite different from Bush-Mosteller in the limiting behavior of the dynamics. The way you analyze this dynamics is using stochastic approximation. Okay? As the reinforcements pile up, the jumps in the dynamics become smaller. Okay? That's what you were objecting to. In evolution, this would correspond to a population that's continuously growing, right, until it approaches infinity, rather than a fixed size population. In learning, well, I don't know, I'm not a psychologist. Right? Roth and Erev say it's, you know, after a while you don't learn anymore because you asymptote. Okay, and the stochastic process then, with high probability, approximates the mean field dynamics more and more closely. Okay, you know how to say that technically with the tubes and the epsilons and everything. Let's go back to our Lewis signaling game. Two states, two signals, two acts with the states equiprobable, and using this form of reinforcement learning. So this is the way to picture it. A sender has one urn for each of the two states, and initially each urn has one ball that says A on it and one that says B, and nature chooses the state. The sender consults the appropriate urn, draws the ball. If it says A, he sends signal A. Right? The receiver has one urn for each signal. If he gets signal A, he consults the urn marked for signal A. It initially has one ball that says guess it's state 1 and one that says guess it's state 2, and he draws out the ball, and that's his guess, right? And then these guys put the balls back in, and if the guess was correct, they put another ball of the same kind in the urn, and if the guess was incorrect, they don't do anything more, right? So that's the learning dynamics. So we have repeated trials of this kind of reinforcement of the balls drawn in a trial. It's fairly complicated because we've got these four urns, but they're all interacting with one another. It can be simplified because of the symmetry of the process, because the receivers are reinforced just when the senders are reinforced, right? Because it's a game of perfect common interest of this kind. If we know the balls in the sender's urn, we know the balls in the receiver's urn. So we can just look at the balls in the sender's urn. Those are four variables. We normalize them, and we get the dynamics living on okay. So this doesn't like graphics in this mode. Sorry. You get the dynamics living on a tetrahedron. Right. Two signaling systems are on edges. They're in the middle of edges, right? There's a curved surface of independence which contains all the pooling equilibria. So there is a Lyapunov function of the mean field dynamics, which implies that you have convergence in the limit to one of these equilibria, one of these zeros of the mean field dynamics. And then you need to prove that there's no convergence to the interior of the pooling surface, and there's no convergence to the boundary of the pooling surface. And it's true, but it takes a little doing to do this. And the result is you have convergence to a signaling system with probability 1. Okay? And this is where it's good to work with the right people.
So if something is reinforced, then both the sender and the receiver put an additional ball in there.
You bet, yes.
So it's always...
Yes, that's the pure common interest of this game. Yeah. Okay, so this is a very strong result for spontaneous creation of meaning again, right? And you could pursue the kind of perturbations that I talked about of the Lewis model in the beginning, right? But I'll talk about something a little different. Suppose instead of two states, two signals, and two acts, you have n states, m signals, and n acts, right? M can be more or less than n, right? So we can have too few signals, so you can't have perfect information about the states transmitted because there aren't enough signals, right? Or we can have too many signals, in which case you might have synonyms which mean the same state, right? Or presumably you might have synonyms that are little used being not reinforced so often and falling out of use entirely in the limit. You don't know until you've done the analysis. Okay, so analysis has been done, and to state the results, we have to introduce a bipartite graph. As before, we need only to keep track of the probabilities of the signal given the state, and we'll consider a bipartite graph that maps a situation, a state, I call state situations also, if there's a positive limiting relative probability, right? So this is all in the limit, right, in order to state the results. And consider this property of such a bipartite graph. Each connected component of the graph has just one state or just one signal. Right? And each vertex in the graph has an edge connected to it. So each state or signal is connected to something, right? That means we don't have signals falling out of use, right? Synonyms will persist if there are more signals than states. Here's an example of a signaling system where the same number of signals and states. Right? Here's an example that's a little different, where we have both synonyms and bottlenecks. Right? In this state, the sender sometimes sends this signal and sometimes sends this signal, right? So if you get either of those signals, it's that state, right? So we've got synonyms for that state. Right? Here we have what I call an informational bottleneck. We've got two states that are mapped to the same signal. Okay? So the signal just tells you it's either this or that. So the main theorem is that if the graph has this property, then this kind of reinforcement learning converges to it with positive probability. Okay. Synonyms are not eliminated in general. Efficiency is possible, but not guaranteed, right? Here we don't have efficient information transfer.
So each signal is I mean, each state leads to one signal only?
No. This state leads to two signals. These are states up top here. These are signals on the bottom.
Now, I was looking at this bottleneck, and so
the bottleneck.
It's because of this divergence possibility, we cannot simply unite the two states into one, right? In the case of the bottleneck.
Well, they're different states. There are different optimal responses to the different states, right? So yeah, that's right. Okay. Are synonyms and bottlenecks something 5 minutes? Oh, you were gonna tell me 15. Okay.
5 minutes and then you have 15.
Oh, my goodness.
For questions, you said.
I'll try not to use it. So how often to get synonyms and bottlenecks? Here we don't have analytic results. These are simulations that Jeff Barrett did. So if we have, and these are all for the same number of state signals and acts, right? And if there are 8 state signals and acts, you get imperfect information transfer in 59% of the time. Right? So it goes up quite rapidly. So if you wanted to look at spontaneous emergence of signaling systems with this kind of learning, for them to start out in a game with lots of state signals and acts, even if it's the same number, it would be very unlikely that you would get an optimal signaling system emerge, right? There may be other stories about how you start with 2, right, and then you add another and so on, but that's a different story. Okay, summaries. First, for the replicator dynamics, even with common interest, emergence of signaling systems is guaranteed only in very special circumstances. With opposed interests, equilibrium may not be reached at all, but rather persistent red queen information transfer might be the norm. And in well-known costly signaling games, such as the Spence signaling game and various costly signaling games in biology, such as the Sir Philip Sidney game, red queen information transfer is a real possibility. Okay, has positive basin of attraction models.
Could you say something else about the red queen?
Well, where the only I'm using this where the only equilibrium is an equilibrium of no information transfer, but you never get to that equilibrium because these sender and receiver are chasing each other around in cycles or in some kind of chaotic orbits, right?
I see by red queen.
Yeah, everybody's running as fast as they can to try to stay in the same place, right? So somebody gets ahead a little bit, and then the other guy gets ahead a little bit, and they go round and round and round. So that's what I'm using it for. Summary for the Moran process and small mutation limit. Things are very different in small mutation limit. You may not be in Nash equilibria. You may spend a lot of your time signaling when pooling is the only Nash equilibrium. And in pre-play signaling, you can have high levels of cooperation. In the stag hunt, where it's a shift in the basins of attraction of the cooperative equilibrium, which is an equilibrium, Nash equilibrium, or the non-cooperative equilibrium, and even in the prisoner's dilemma, where the cooperative behavior is not a Nash equilibrium at all. Right? And the more signals, the better. In prisoner's dilemma, it's like a secret handshake business where there are a lot of secret handshakes, right? And somebody comes in with a secret handshake, cooperates with his own guy, defects against the native population, who are all nasty defectors, right? They take over, right? But then somebody comes in who can mimic the secret handshake and defects against everybody, and they take over. But then somebody comes in with a new secret handshake, right? And what happens in the limit as this process goes on, it seems very complicated, right? But in the small mutation limit, you can actually solve these things. Right? And you can spend a lot of time cooperating if you have enough signals. Reinforcement learning. In the very simplest Lewis signaling game, reinforcement always learns to perfect signaling, perfect information transfer. In more complex Lewis signaling games, results are more complicated. Suboptimal signaling can happen, right? So my tagline is that dynamics has some surprises for us. Thank you.
Now, we have 12 minutes for questions.
I'm wondering, I've been thinking about a problem that involves the cycles that you see in games like the hybrid, the cycling around the hybrid equilibrium costless signaling, as well as the cycling that we see in a opposed signaling, like with the matching pennies game. Can you get? I'm wondering how how regular it is to get these cycles that go all the way around. I mean, do we ever, how hard is it to get these cycles to spiral inward or to spiral outward away from the equilibrium?
Well, matching pennies, right? As I said, it's not structurally stable, right? So in matching pennies, a small perturbation of the vector field will either let the cycles spiral in to the equilibrium or spiral out, and who knows about the real world, but in the differential equations, they just get closer and closer to the boundary, right? Yes,
If
Don?
you ever see a continuum of something like that, of a circle or of equilibrium, it's not structurally stable. That was pretty clear when he was talking about pooling equilibria at the beginning. So if you see circles, you know, all circles, and there's a continuum, a slight perturbation will make it go one way or the other. And you can perturb it one way or the other to either get it cycling going in or cycling going out.
And that's done for chaos, or that's done for...
That's
So
just a general theorem.
yeah. So we shouldn't trust that so much, right? Because it's very special, right? That's why I moved on to the second example, which is Hamiltonian chaos in the two-population signaling game, and that is structurally stable.
You had a statement about structurally stable chaotic type behavior. It's a three-dimensional system, R3. Is that chaotic in the sense that it looks wild, or is it chaotic in the sense of usual definitions of dynamical chaos?
The one that I showed you.
Where you had along the diagonals ones, and then you had 0.5s, and you had minus ones, and then you wrote down the replicator dynamic game for that. Is it truly chaotic in the sense of
It's-
a homoclinic point or something like that, or not?
It's truly chaotic.
In the sense of appearance.
Yeah. The chaos is deduced not only from the way it looks, but from calculation of Lyupanov exponents
Okay.
on orbits, although that's done by numerical integration.
Numerical methods. Okay, so in other words, because when you had that, I was just going down through, you had the diagonals, the ones, and you had 0.5s, and you had
Mhm.
minus ones. And so you had a permutation type matrix, which you had there. And so indeed, you do have an unstable point, and your unstable point for the equilibrium is going to have a stable and unstable manifold. And if they cross, they intersect, then you're going to have true chaotic, and that will be structurally stable. That's just curious as to whether anyone proved that or not.
Yes?
Just a comment or questions. So I think all these dynamics equation models deterministic. I mean, what happens if there's no stochastic noise? So that it's not
Well-
just follows this equation.
Well, so there's three parts to my talk. First part was deterministic, right? That's replicator and selection mutation dynamics. Those are differential equations, right? Second part is the finite population model, and that's stochastic, right? And the third part was reinforcement learning, and that's stochastic too.
So okay, then the first part, the replication dynamics, is there any reason why you want to consider on the deterministic case?
Well, the story is you're assuming this is an infinite population, or close enough to infinite that it's not so bad to treat it as if it was the limit, right? So that now your probabilities are population frequencies, right? And what you expect is what you get. Law of large numbers. And if you want to say, no, wait a minute, that's a finite population, then you can move to one of the other models. If you have something like a Moran process and you throw in very big populations, right, it gets close to replicator dynamics.
Partial answer to this question, if it is structurally stable, in other words, and this is well defined in mathematical terms, that if you perturb the function, x dot equals f of x, and you throw in an epsilon g of x, and we have no idea what that epsilon g of x is, but dynamics is somewhat, in a well-defined way, it's the same. Then what happens is, if you throw in a stochastic with a very small stochastic effect, it will, what Brian pointed out, will remain. But if you have a large stochastic effect, and you have a couple of basins of attraction, well, that large stochastic effect can jump you from one to another. But Peyton Young has looked at some of those type of things, which you can handle it in the effect that I just got you telling you. One of the reasons you don't look at them is because those equations are so damn hard.
I'm going to try something. I'm curious, I always have been curious. What is there, generally speaking, that makes these kinds of problems attractive to philosophers? So you mentioned a lot of philosophers in the history. Is it Wittgenstein or what is it?
No, I didn't mention Wittgenstein, but I could have, I suppose, in the investigations. So this is a philosophical question. Where does meaning come from? Meaning of language, or meaning in signals, or whatever you want to call it, right? I mean, people, animals, they're signaling, right? And it conveys some information. How is this possible if you start out without it, right? If you just have grunts or some things you can do that another organism recognizes, right? And there are really two traditions if you want to trace it back, right? There's a tradition that says, look, somehow meaning arises by a chance process, right? With some dynamics and something, you know, sort of kind of reinforcement. I mean, they don't say this, but, you know, and it goes way back to Democritus, this idea. And there are other people who say, no, meaning is somehow, there are meanings, right? There are propositions and they're somewhere, right? And somehow I mean, they're there in your head, and somehow you learn to correlate things with them, right? And that's Plato. And these traditions go on. So to look at this, it's a philosophical question, right? But it hadn't been looked at really very well dynamically until recently. So that was the motivation that got me into it. But then you start doing dynamics of these things and you find out so many interesting things happen that it's hard to stop.
Okay, thank you, Brian.